Welcome back. We are starting continuous time, but still discrete state space Markov chains. And to prepare for this, we have been reviewing continuous distributions such as the exponential and the gamma. And today, I have one more distribution to review, which is actually not continuous, and that is, I need to share my screen, but that is the Poisson distribution. Because actually, our very first continuous time process is going to be something known as a Poisson process. So the Poisson distribution is going to be important. Okay, so this is not a Poisson process, which is something evolving over time. This is just a random variable. It's discrete, and it is the Poisson distribution, which I'm sure you've all seen. I mean, if you've had any sort of probability, which is a prereq, then you should have seen this, which is why I'm going to go kind of fast, but come to my office hours and I'll talk about it as slowly as you want. So we write X, squiggly line has the distribution, Poisson, and it has a parameter that's almost always called lambda. And this is something greater than 0, and it's a parameter for this model, much like the p for the geometric or the mu and sigma squared for normal. And what is going on? I gotta solve this problem right now because I couldn't see. Once I start talking, my chat window disappears. And then last class, I couldn't see the chat the whole time. Give me a sec, sorry. Okay, so the Poisson distribution, see, I lost my chat again. So this is a discrete distribution. And the probability mass function, or the probability that x equals some little x, is e to the minus lambda, lambda to the x over x factorial. And this holds for x equals 0, 1, 2 on up. And it's going to be 0 otherwise. So there's going to be a lot of kind of E exponential calculations coming up. And I think it's going to be useful for you to recall that you can get a Taylor series expansion of e to the x, and it is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., which we can write as the sum as n goes from 0 to infinity of x to the n over n factorial. So I think you might find it useful to recall that for what's coming up. Yeah, so I'm just going to say a couple of things about this distribution, and then we'll get into using it. So one thing is the expected value of x. So this is, well, let's do it. The expected value of x is going to be the sum over all x of x times this probability. And of course, this sum is 0 in a lot of places, so I only need to sum it as x goes from 0 to infinity of x e to the minus lambda, lambda to the x over x factorial. This computation and the next one that I'm going to skip occurred a couple of lectures ago, because when I first started reviewing the exponential and then the gamma, I believe I put up notes that had all three of these distributions, but then stopped reviewing for a little bit because it was, boring. So I think you have this already in some notes that are like maybe 2 lectures back if you don't include reviews. All right, so when x is 0, then this whole thing is 0. So I can write this as the sum as x goes from 1 to infinity of x e to the minus lambda, lambda to the x over x factorial. And I can cancel the x with the x in the x factorial. So I've got the sum as x goes from 1 to infinity, e to the minus lambda, lambda to the x over x minus 1 factorial. And so I could use the fact that e to the x is the thing I put in the box to sum this up. That is, I could pull out the e to the minus lambda and reorganize things a little bit. But I think I'm going to use my usual integrating without integrating, or in this case, summing without summing trick, which is to make this look like a PDF again. So I see the x minus 1 factorial, and I kind of want an x minus 1 up here. So I'm going to pull out a lambda. And then I have e to the minus lambda, lambda to the x minus 1 over x minus 1 factorial. And when you plug in x equals 1, you get you get 0 in that exponent and 0 in that factorial. So this is the same thing as lambda, the sum from 0 to infinity, e to the minus lambda, lambda to the x over x factorial. And that is the Poisson PDF again, or PMF, summed over all values. So that's 1. So we get lambda. Okay, so I'm not going to drag you through the variance. I'm just going to give you a hint if you wanted to compute the variance by yourself. So let me go back to my bullets. The expected value of x we just saw was lambda, and the variance of x also turns out to be lambda. And if you wanted to compute this for yourself, I would use the fact that, one way to write the variance is the variance of x is the expected value of x squared minus the expected value of x all squared. So we need this guy, the expected value of x squared. And going for that is actually kind of hard because canceling with the factorial, if you have 2 x's in front, you can cancel one of them and the other one is still out there. So I would try looking at the expected value of x times x minus 1, because if you write that out, that's going to be the sum of x minus 1 times the probability mass function, and the x minus 1 will cancel nicely with that factorial. And then you can use the fact that this is the expected value of x squared minus the expected value of x, and that that this is lambda, and you can solve backwards for that expected value of x squared. If you care, this course uses surprisingly little variance. Any questions on anything? Okay, we saw last time that the minimum of exponentials is another exponential. And specifically, we saw that if x1 through xn are IID exponential with rate lambda, so y defined to be the minimum of x1 through xn is exponential with rate n lambda. And so I talked about this from a sampling point of view, going over to my graph. If you start sampling exponentials, they're going to mostly be piled up over here because that's where most of the area is. And so if you grab a sample of size, say 20 x's down there, and you look at the minimum, you get a number. And then if you erased everything and grabbed another sample of size 20 and you looked at the minimum, you looked at the minimum again, you would get another number somewhere down here. And if you collected all those minimums and made a histogram of those are going to be really kind of piled up in a really kind of spiky way at 0, which turns out to be another exponential. And it starts way up here at n lambda, way up if n is large. Okay. So we need one more tool, kind of. We need 3 results. And I debated whether or not to prove them in here because it's really more of a math stat move. But we need to know about sums of certain distributions. And so I'm going to be really, really brief about how I show this, and that is with moment generating functions. And you, in fact, will not really need, I don't think you'll ever need to use them in this class. And if you want to ignore this and just take my 3 bullets at the end, the 3 things I'm trying to prove, that's fine. It kind of pains me just to throw them up there as facts. So if you have a random variable x, the moment generating function that I'm going to abbreviate MGF, I'm going to call it M. It's going to be of some variable, usually T's and S's are used, it doesn't matter. And it's defined to be the expected value of e to the tx. And if we have multiple random variables, then we might want to use a subscript on the moment generating function to say this one goes with x and not y. So this is the definition, whether x is discrete or continuous. It just computing this expectation is going to be different when the random variable is discrete versus continuous. So if we have x continuous, then the moment generating function, which is this expectation, this is the integral of e to the tx in front of the PDF or x, and you integrate over the whole world. Yeah. And so here's where I just said I don't like throwing facts up and then not proving them, but this is gonna, you can't really do this right now. You might recognize this as looking kind of like a Laplace transform, or if I put IT in place of T, a Fourier transform. And if you've never seen those, that's fine. They're not prereqs for this class, which is kind of why I can't prove this. But you might recognize this as manipulable into a Laplace transform or a Fourier transform. And don't worry if you haven't heard of those things, but if you have, then maybe you've heard of an inverse Laplace transform or inverse Fourier transform. And so there actually is an inverse formula that, given a moment generating function, can actually get you this PDF back. And it's not nice, and it's not closed form. It probably involves a limit and a sum or an integral that you can't actually do in closed form. So it's not really useful for finding PDFs given moment generating functions. But again, I can solve for this given this, and there's one solution. And my point is that moment generating functions uniquely determine a distribution. For example, how are you going to know if something has an exponential distribution? If you write down the PDF and it looks like lambda e to the minus lambda x, then it has an exponential distribution. We usually identify them by PDFs. But I'm claiming here that if you have two random variables with the same moment generating function, they must have the same PDF and therefore the same distribution. So it's called a moment generating function because you can use them to generate things called moments, which I don't even want to talk about. This is going to be really brief, but moments of a distribution are these expectations, the expected value of x, expected value of x squared, x cubed, on up. These are known as moments of the distribution. And you can get these from a moment generating function by taking some derivatives and plugging in t equals 0, and kind of don't care about it at all for that. But I do care about the fact that it uniquely determines the distribution. What do I mean by that? Let's look at the Poisson. So here's an example. And that is huge, so I can't not write this. The moment generating function uniquely determines the distribution. So as my first example, he's in this little bin next to me, and he's got these baby crickets and mealworms, and they're all riding around on him like little birds on a hippo. They're on his face. He doesn't care. So suppose that x has a Poisson distribution with parameter lambda. Let's find the moment generating function for x. So I am going fast because really I just want the result in the end. I'm just trying to give you at least part of what we can show in this class. This is going to be the expected value of e to the tx. And so for a discrete random variable, this is going to be the sum over x of e to the tx times the probability x equals x. And in particular, for the Poisson, this is going to be the sum as x goes from 0 to infinity of e to the tx, and then the probability mass function, which is e to the minus lambda, lambda to the x over x factorial. And when you raise something to a power and then to another power, like e to the a to the b, you get to multiply the powers. And you can do that in reverse. So I'm going to rewrite the e to the tx as e to the t raised to the x, and then I'm going to combine it with the lambda to the x. So this is the sum from 0 to infinity of e to the minus lambda, and then lambda e to the t to the x over x factorial. And this is starting again to look like kind of a Poisson probability mass function. It's just that in place of what used to be lambda to the x, we have this whole thing to the x. So if we plug that whole thing, that lambda e to the t, in for every lambda, then we would actually have a probability mass function that sum to 1. So I'm going to do this. I am going to take out the e to the minus lambda, because that's kind of not what I want there. And I'm going to put in an e to the minus lambda e to the t, just because I'm trying to mimic the Poisson distribution. But I can't just do that. So I'm going to compensate by putting an e to the positive lambda e to the t. Gotta be really careful. My lambdas can look like x's. Lambda e to the t out here. And now this is the probability mass function of the Poisson distribution with parameter lambda e to the t. And so the entire sum is 1. 1. Give me chat. Someone let me know if there's some like hanging question out in the chat, which I can't see again for some reason. Okay, so if that thing in the circle is 1, then I can rewrite, or I can combine these guys into an e to the lambda times e to the t minus 1. This is the moment generating function for the Poisson distribution. And because we have things to a power to another power, it's usually written like this. So if x is Poisson with parameter lambda, then the moment generating function is exp, so we can write it on a line, lambda e to the t minus 1. And this holds for any t, but some moment generating functions, when you go to compute the sum or the integral that you get, they will diverge or blow up for certain values of t. So sometimes you might see a moment generating function written down and it'll say, don't write this, this is wrong, but it'll say something like, if t is less than lambda. That's actually not right here. But sometimes there are restrictions. It will only, converge for certain values of t. Okay, so what is the importance of this? The importance, I said, was to determine distributions, but specifically to determine distributions of sums. I'm going to show one thing, and then we'll look at the sum of the Poissons, and then I will write the 3 facts that you really need to know, and then try to scatter the proof. I'll put the proofs in the notes and not out here. So we can go back to talking about continuous time Markov chains. So I don't know what to call this. Not an example, it's like a fact. I don't know. Check this out. So suppose I have x1 through xn, IID, independent and identically distributed with moment generating function m sub x, or maybe, this x, there's no x in the problem. This is supposed to be representing a generic one. But if it's upsetting to you to see that m sub x and there is no x, I could write m sub x sub 1. So it's the moment generating function for the first one, but they're all exactly the same. Not that the random variables are the same, but those expectations are the same for all of these. So they all have a common moment generating function. And then I'm going to let y be the sum as I goes from 1 to n of x sub I. So check this out. The moment generating function for y is the expected value of e to the ty. The y is the sum of the x's, so I'm going to plug that in. I can pull the t inside the sum, and then e to a sum is a product of e's. So this is the expected value of the product as I goes from 1 to n, e to the t xi. So if you've never seen that symbol before, this is just a product like the summation symbol is a sum. And then by independence, we know that you can pull For example, if you have X and Y independent, you can pull it apart into the product of the expectations if they're independent. And also, if you go back and look at that chapter 1 of the notes, I talked about this kind of thing for a simple like function of X times a function of Y, and you can factor expectation. My point is, going back to the moment generating function, this is going to be the product of all of those individual expectations. And then this is going to be the product as I goes from 1 to n of the moment generating function for xi to the t. And this actually would be where you stopped if they were not identically distributed. I need to write, this is super important. I'm going to put independent on that equal sign there. If they're not identically distributed, then at this point, you can find the moment generating function for y by plugging in the individual moment generating functions. But if they are identically distributed, did I just say not independent? This formula that I wrote right now requires independence, but it does not require them to be identically distributed. But if they are, then we can take it a little further. So by identicalness, this is just one moment generating function because they're all the same. Multiplied by itself, by itself, by itself, you get the nth power. So the moral of the story is, if you are summing up IID random variables, the moment generating function of the sum is the moment generating function of one of them raised to the nth power. So let's use it for the Poisson, and then I'll write the other facts down, and then we move on to our first continuous time Markov chain. Okay, so let's try to find the sum of Poisson random variables. So suppose I have x1 through xn, and they're independent, identically distributed Poisson with parameter lambda. So today we saw that the moment generating function for one of the x's, again, my x without a subscript is representing a generic one, or we can write x sub 1 to say it's the moment generating function for the first one, which is the same as all the others. So we just showed that this was e lambda e to the t minus 1. And now I want to look at the distribution of the sum. So if I let y be the sum as I goes from 1 to n of the xi, then the moment generating function for y, because these guys are IID, is the moment generating function for one of them to the nth power. And that is going to be e of all of this stuff to the nth power. And when you raise something to a power and then to another power, you do get to multiply the exponents. And this exp is this thing raised to this power, which is then raised to this power. And so we get exp n lambda e to the t minus 1, which we recognize because we've only seen one other moment generating function. We've only seen one total. This looks just like the original. So this looks just like this, but there's an n lambda in place of the n. And so this is the moment generating function for a Poisson with parameter lambda. So this is the moment generating function for a Poisson with parameters n lambda. And because it uniquely determines the distribution, this is enough to say that y has a Poisson distribution. So before I write that, let me just down here say, this is the moment generating function for a Poisson with parameter n lambda. And so now I will slow down, unless, is there anything you want me to clear up? I'm gonna recap this result right now with two other bullets of results that we're gonna need. Okay, so here are the things. I'm really at a loss today for coming up with subject headings. So the first thing we just showed is that if you have x1 through xn, independent, identically distributed Poisson random variables with parameter lambda, this means that the sum as I goes from 1 to n of xi is Poisson with parameter n lambda. Okay, so the two other things that we could show if, I'm not gonna say if we have the time, we could take the time, but this is really getting away from Markov. And again, I'll put it in the notes, is that if you have x1, oops, you have x1 out through xn, IID exponential with rate lambda, this implies that the sum has a gamma distribution. And the first parameter is the number of things you add together, and the second parameter matches that of the exponential distribution. And finally, there are plenty more, but these are the three we care about. If you start with gammas and add them up, you get another gamma, which you can kind of think of as adding up a whole lot of exponentials. So if x1 through xn are IID from the gamma distribution with parameters alpha and beta, this implies that the sum from 1 to n of the xi is gamma n alpha beta. And I would show all of these by finding moment generating functions for the exponential and gamma distributions, and then doing what we just did to show that if you take the exponential moment generating function and raise it to the nth power, it matches that of a gamma. And if you take the gamma moment generating function and raise that to the nth power, it matches that of another gamma. I guess I'm going to write these others up in the notes, as I said. Just one thing I want to mention before moving on is that these moment generating functions, you know what, I'll just put that in the notes. You use moment generating functions if you come from any other sort of stochastic or probabilistic background. But in Markov processes, people use things called probability generating functions more than moment generating functions. And I think I'll have that. So there's no homework due this week, but when the homework comes out this week, I think I'll just have an exploratory problem on probability generating functions rather than talking about them and what they can do for you. All right, we're back to continuous time, but still discrete. I'm putting this in parentheses because you should assume it's discrete, a discrete state space. Markov chains. And I did go through this whole discussion about, oh, if it's continuous time, you call it a process. But then again, everyone always abbreviates this CTMC. And I've never seen anyone abbreviate it CTMP for process. Now, I already defined the Markov property, I think, way back. And that was, I'm going to write it really sloppy here without the fix an I, fix an S1 through Sn, fix a, but the Markov property says that if you have a like 0 less than or equal to some real number S1, less than S2, less than Sn, less than S, less than T. So this statement, because I'm being sloppy because I wrote it down in the past, has to hold for all n and for all choices of these real numbers. We need the probability that xt is equal to some j. Now, that statement makes sense because it is a discrete state space. So it's a discrete random variable. But you'll notice that I went to the continuous notation. So you could absolutely write this as x sub t, just like we wrote the x sub n. But I like to kind of really differentiate the notations. So the probability, given that x sub s is I and x sub n, x sub s, x of s sub n is some I sub n, all the way down to x sub s1 is an I1. This is just going to be the probability with the last piece of information. So this is what it means to be a continuous time Markov process or chain. And so let us define a very boring Markov process. You know what? It's not Markov necessarily. So I'm going to define a more general process called a stochastic process, right? Remember our day one, stochastic means random and process means something that's changing over time. So I'm going to define a counting process, which is a type of stochastic process that is not necessarily a Markov process. So we're going to use these a lot and kind of give them their own notation rather than using a generic x of t. So a counting process. I'm going to use brackets to denote the whole process, not a particular single random variable. And I'm going to use a capital N of t. And then I'll put this little subscript here telling me that t, which is continuous in this case, is running from 0 to whatever. I mean, it's all non-negative real numbers. So this is it doesn't have to be continuous time, but the way I've written it, it is, let me not write continuous time here, is a stochastic process, not saying it's Markov, that counts a number of events that occur up to and including time t. So you're just kind of going along in time and you have an event and they're occurring at kind of random times that are going to be continuous random variables for us. And you just run along if you want to draw this process with those t's, you just run along nice and flat and then you jump up by one. Yeah, and then you jump up by one, and then you jump up by one. This is what a counting process looks like. It looks like a step function. And it's not necessarily Markov. Okay, I'm ready to define the Poisson process, which is going to have a major role in the entire rest of this course. So I'm going to define it in 3 different ways. I think only one way today, and I'll show you the equivalence between the 3 definitions. And I think each one of them will have value to you in different situations. So this is definition 1 of a so-called Poisson process. And again, there will be 3 different definitions. So we're going to start with the counting process and then make it have some special properties. So that's how my definition is going to start. The counting process, N of t. So I know I say this a few times. I won't say it again, I hope. But when I write this, that is the random value at time t. And when I put brackets around it, it's referring to the whole process. This is a Poisson process. And it has a parameter known as a rate parameter. And I'm going to call it lambda. So with rate lambda, which needs to be greater than 0, if 3 things happen, at least in this definition. I've got 3 things in all 3 definitions. So the first is not really important. You could actually change this, but it is convention to always start the process at time 0 with 0 things counted. Like you start at time 0 and you wait for something to happen and you start counting. So this is a convenience and you really could start this process at a different number. Okay, the second thing is that it's known as the independent increments property. It's like way too many letters. Independent increments property. So this says for any time points, I'm going to take t, like a t0 to be 0, and this is going to be less than some t1, less than some t2, out to some tn. The increments of the process, and I'll find that, the increments are independent. So by increments, I mean how much the process is incrementing. So the number of arrivals to this process, if you're thinking of it as arrivals at time t1 minus the number at time t0, and the number at time t2 minus the number at time t1, all the way out to the number at time tn minus the number at time tn minus 1. So these are n random variables that I just wrote, and these are independent. So I do need to finish this definition with a triple I, but if we were in class, I would walk to the other side of the board and draw this picture that I'm going to erase pretty quickly. So I did not finish my definition. There is a triple I, but as this process goes along, it jumps up, maybe we'll even fill in uh, vertical lines. So where you go, the fact that you're jumping up to this value at this time is totally dependent on the fact that you were at this value at previous time. The counting process, definitely the values are not independent. They're very dependent. They're accumulating things. But the increments are so each of these things I'm circling are the number of arrivals in the interval from, and I'll be more specific eventually, but from T0 to T1, and the number of arrivals between T1 and T2. And at the end here, the number of arrivals between time Tn minus 1 and Tn. So if you blocked off different regions of time here, the number of arrivals, the number of steps up in this region is going to be independent of the number of steps up in here. Third thing, why do we call this a Poisson process? Because it involves the Poisson distribution, although it doesn't have to, because my other definitions don't. But what is this one doing? This is triple I of the definition. So this says for any real number s greater than or equal to 0 and real number t greater than 0, we're going to look at the number of arrivals between time t and time t plus s. So that's going to be, I'm going to write s plus t. So this is the number of arrivals. Now, I didn't finish what this statement is, but we defined the counting process to be the number of arrivals up to and including time t. So this is going to be a number of arrivals up to and including time s. Not that you're going to get an arrival there because you have this continuous time thing happening. And then we want to take the number of arrivals at some later time and subtract off the number of arrivals up to here. So this is going to be the number of arrivals in the interval open S to closed S plus T. Because again, it was everything in here down, and then I subtracted everything from S down, including S. Okay, but I never stated property 3. So here it is. This has a Poisson distribution. And the parameter, so at the beginning of this definition, I said we're defining a Poisson process with rate lambda. And this is now is a Poisson random variable. And it's lambda times t. And t is the length of the time interval. So bigger time interval, higher rate in that Poisson process, you're going to get more arrivals if you look at a bigger interval than you do with a smaller interval. This is definition 1. Everybody okay? More specifically, and you can write this after your definition or include it as part of triple I. So i.e., the probability that ns plus t minus ns equals some k, this is going to be e to the minus lambda t to the k over k factorial, where k equals 0, 1, 2, on up. And You'll notice in this definition that the ultimate distribution over on the right side doesn't depend on S. So it's sort of like you can look at the timeline anywhere. You can start at any S, and then the number of arrivals in the next t units of time depends on the length of the interval, but it doesn't depend on where S was. So we actually also call this idea, this is something a little more specific. The Poisson is a little more specific than what I'm about to write, but this is a stationary increments property, which is saying the distribution of ns plus t minus ns doesn't depend on what s you started with. So again, picture the interval where you've got like open at s and closed at s plus t, and you can slide that around. As long as you keep it with length t, you'll have the same distribution for the number of events in that interval. Yeah, it kind of doesn't. So the definition 2 is going to be rephrasing this all in terms of the exponential distribution. One thing we have is, I guess I'm finally out of this definition, but note that n, the number of arrivals by time t, is the number of arrivals by time t minus the number of arrivals at time 0, as long as you use that convention of starting with this equaling 0. So those two time steps are an interval of length t. So this is a Poisson distribution with a parameter lambda t. So once you fix time, the number of arrivals is a random variable, and it has, in this case, a Poisson distribution, and we know a couple of things. We know the expected value of n of t is lambda t, because that's the mean of this Poisson distribution. And we know the variance of n of t is lambda t, because the Poisson distribution is just nice like that. The variance and the mean are the same. So next time, I want to start off with reviewing conditioning on a continuous random variable. It'll be pretty quick. And then we're gonna prove that for this Poisson process, the inter-event times are always exponential. And then we're gonna lead to this definition 2, which says that's actually an if and only if. So I'm gonna replace, I might tweak double I a little bit, but triple I is gonna move from talking about the Poisson to talking about the exponential. And I'm really out of time, but my third definition is the absolute favorite, because there's like no structure in there, but we still get the Poisson process, which is why these are so important. They appear everywhere because they're actually not assuming a lot, even though it looks like it. So thank you. I'm out of time. This is my office hour. Bye. Cut. Select. Right. This is Zuko that you guys named the Argentine red tegu. Ah.